Now that we have looked at the normal equation of a plane in R3, we're going to look at the vector form of a plane in R3, just like we did for lines. Now, you'll recall that for a line in R3, the vector equation is of the form xyz is equal to, this is a point, and to that point we add a multiple of a vector pointing in the direction of the line. So that's why we have this lambda v, where lambda is any real number. As an example, you've got xyz is 1, 2, 3 plus lambda times 4, 5, 6. Now 1, 2, 3, that's our p0 right there. 4, 5, 6, that's a vector pointing in the direction of the line, illustrated in red here. And when we add the two, although 1, 2, 3 is a point, we can associate that point to a vector starting at the origin, which is here, ending at p0. And then with that, we add lambda v. So the sum of those two vectors gives us a vector pointing, starting at the origin, but ending at a point that's on the line. So that's how we get p0 plus lambda v. That's equal to p. Now we're going to try to generalize this to get vector forms for planes in R3. Now imagine I've got this plane here, okay? So now it stretches in all directions. So I've just illustrated part of this plane, okay? So you have to imagine that this drawing is in 3D. You have to put your 3D glasses on, okay? It's some plane, so so imagine I've got this point again, p0, on the plane. Now to move on this plane, what I need are two vectors. Now u and v, okay, that are not parallel, but they allow me to move anywhere in the plane. So in fact, these two vectors, what they do is they create a mesh, right? Remember, they create a mesh for that plane, and I can move on that mesh to reach any point that I want in the plane. So I've drawn the mesh for integer multiples of u and v. Now for making this even easier to see, what I've done on the right here is draw this mesh on the screen. So imagine the plane now is the screen. So I've got two vectors u and v, and for convenience we place them so that they both start at p0, which would be some given point on the plane. To reach any other point on the plane, let's say point P, I'd have to move on the mesh created by the two vectors, u and v. So what I would do is, to get to a point P, so P would be here in this case, I would start at p0, and then I would add some linear combination of u and v. So those are scalars or real numbers. They don't have to be integers, but for simplicity here, I've chosen a p so that s and t are actually integers. So how do I get to p? Well, I have to travel from starting at p0, I have to travel 1 twice along v, so 2v, but then I need to go against the direction of u 1 times. So to get there, this is minus u that I'm doing here. So there's a minus u here to get to p. So I have here a linear combination of u and v, and that linear combination in my specific example here would be minus u plus 2v. But you realize that if I want to get here, for example, to that point, I don't know, q would be what? It would be p0, and I need to go all the way here, so that's what, 3/2 of u, and this is 1/2 of v right there. This is 1/2 of v, 3/2 of u, 1/2 of v. Okay, so though, like I said, those don't have to be integers. It could be any real number actually. So that's what I'm trying to illustrate here on this drawing. So to get to P, you first go to P0, and then you do some sort of linear combination of U and V so that you can move on this plane and get from P0 to P. So P, right, would be P. You go to P0, so that's doing this thing here. And then you do some linear combination of U and V to move within the plane. Okay? So maybe I'll show you an example. Consider a plane with equations x equals 2 plus 3s minus 4t, y is 6t minus 4 plus 2s, and z is t minus s, where of course it's, even though it's not written, it's assumed that s, t are real numbers. Okay, we want to find a point on the plane and two vectors contained in the plane. Okay, so to do this, we're gonna first see that these equations, they give us the equation of the plane in vector form. Well, first of all, so let's say solution. See, I could regroup these equations into a single equation by putting it in vector form, right? So this is 2x is 2 plus 3s minus 4t, 6t minus 4 plus 2s, and t minus s, like that. But the way I want to write it down is, I want to write it as a constant part, so a point, plus a linear combination of two vectors, where s and t are the coefficients of that linear combination. So for the point, what I'm looking for are constants, right? There's no s and t present in the expressions for my point, so I have to look at what are the constants in each expression. There's 2 minus 4, and here hiding 0, right? So as if I have a plus 0 there. So it's 0, minus 4, and 2. Those are my constants. Okay. What are the coefficients for s? Well, 3, 2, and minus 1. And for t, I have minus 4, 6, and 1. Like that. So that's kind of P0 plus S times U plus T times V. Okay. Now P0 is a point on the plane, and U and V are the two vectors contained in the plane. Okay, just like on my drawing before. U and V are contained in the plane. P0 is a point on the plane. So so P0 is equal to 2 minus 4, 0. And B, two vectors contained in the plane, U equals to 3, 2, minus 1, and V equal to minus 4, 6, 1. Of course, these answers are not unique, so the P0 is the easiest one that I get. It's by assigning both S and T to 0. If I do that, I get P0, but if I assign S equals to 1 and T equals to 0, I'd get some other point. I would get the point 5 minus 2 minus 1. So I can get, actually, just like for lines, infinitely many points from that equation, right? I can assign my favorite values, sorry about that, to S and T. And I can get infinitely many points. So that would be another question. Like, give me like 5 points, 5 different points on this plane. You just assign 5 combinations of values to S and T, and then you get 5 points. Same goes for the vectors. U and V, they're contained in the plane, but if I multiply U by some scalar or V by some scalar, I'd obtain other possible vectors. And I could get any linear combination of u and v to create another vector that's contained in the plane. Finally, a little note here. Let's say I have this plane here, right, given here or here, right? How do I get from vector form to the general form? What's the general form again? It's like this, form like that. How do I go from the general form to the vector form? And how do I go from the general form? How do I go from the general form to the vector form, and from the vector form to the general form? Those are two interesting questions. We're gonna see in chapter 1 how to get from the general form to vector forms, and at the end of this chapter we're going to see how to go from vector form to general form. Now, to go to general form, I need essentially a, b, and c, which in a, b, c are the coefficients of a vector that's perpendicular to the plane. So you see in my drawing, what I need would be a vector n that's perpendicular to both u and v. That's what I need, because if I have p0 and n, I can write my point normal form, and then from that I can just expand and get the general form. But my point is I need a vector n that's both perpendicular to u and v. So perpendicular to u and v means that n dot u must be 0 and n dot v must be 0. So we're going to need to find a vector that satisfies both of these equations. And we're going to see this in 3.5. In 3.5, we're going to see how to get a vector that's perpendicular to two other given vectors. But right now, we're not ready yet. So planes for now, they're given either in vector form or in general form or point normal form, which is almost the same. But we don't know how to go from one to the other. We can do that with lines, but not with planes yet.